This is section 6.5. We're going to be talking about properties of logarithms. So remember, a logarithm that's an A. So log A of B equals Y if and only if A to the Y equals B. So, if we do all of these, 5 to the something, which we'll call Y, has to equal 1. Well, the only way that happens is if Y equals 0, because anything to the 0 power is 1. So 2 to the Y equals 1 when Y equals 1. Remember, a log with no base is really a base 10, so 10 to the Y equals 1, or Y equals 0. Oops, and I screwed up on part B. That should be Y equals 0 also. Remember, natural log, ln, is base E, so E to the Y has to equal 1, which means Y equals 0. Okay, let's do it again. So 5 to the something has to equal 5. Well, that's if the exponent's 1, right? Same thing, 2 to the Y equals 2 when the exponent Y is 1. 10 to the Y equals 10 when Y equals 1. And E to the Y equals E when Y is 1. So what do we know? Log base anything of 1 equals 0. And log base A of A, so if the log is the same as the base, if the argument is the same as the base, then it equals 1. So, based on that, and the property of logs, 2 to the log 2, those essentially cancel each other out, and we're left with pi equals m. Likewise, here we have 3 to the m equals 3 to the negative 5. Remember, if the bases are the same, the exponents have to be equal. So m is negative 5. So a raised to the log base a of m equals m, and log base a of a to the r power is r. I'm moving to the next page now. So, here we have some more properties of logs. We're going to do a little exploration here. So, log of 100 times 10. If you put that in the calculator, you get 3. And if you put in log base 100, you get 2. If you put in log base 10 of 10, you get 1. So you can see that they're equal. Same thing here. Log of 1,000 over 100 is 1. Log of 1,000 is 3. Minus the log of 100 is 2. So that checks out also. Okay, log base 10 of 10 cubed is 3. And 3 times log 10, which is 1, is 3. So that property works out also. So what that means is that log base A of m times n is log base A of m times, plus log base A of n. The division works out to be log base A of m minus log base A of n. And for log base A of m raised to the r power, we bring the power down in front and multiply by the log base A of m. So, use the laws to simplify the following. Well, we already know from the previous page that as long as the base of the log is the same thing as the base of our exponent and the log is in our exponent, that they cancel each other out and we're just left with the argument of the log, which is 18 in this instance. Same thing here, 2 raised to the log base 2 of negative 5 is negative 5. Log base 1/2 of 1/2 to the 20th. Remember, we can bring the 20 down in front. And then we have log base 1/2 of 1/2. And remember, anything when the base of the logarithm and the argument are the same, they're 1. So we have 20 times 1, which equals 20. And for the last one, remember, natural log has a base of e, so this is 3 natural log of e, because we can bring the exponent down front, which is 3 times 1, which is 3. Now, we're going to use the laws of logarithms to find the exact value without a calculator. So, using the rule number 6, going backwards, if we have the logs with the same base and they're subtracted, we can make that a division problem. So, log base 3 of 24 over 8, which is log base 3 of 3, which we know equals 1. Okay, same thing on this one. Log base 8 of 2 over 128. Again, changing the subtraction of 2 logs since they have the same base into a division. So we have log base 8 of 1 over 64 so that's 1 over 8 squared, the 1 over 64. So we have log base 8 of 8 to the negative 2, which is negative 2 log 8, because we can bring, log base 8 of 8. So we can bring the exponent out front again. which is -2 times 1 or -2. Okay, moving on to the next page. We have 6 raised to the log base 6 of 3 plus log base 6 of 5. So that is, if I can figure out where the cursor went, there it is. So using the multiplication rule, where the addition of 2 logs with the same base, we multiply their arguments. We have 6 to the log base 6 of 3 times 5, which is 6 log base 6 of 15. And of course the 6 and the log 6 cancel each other out, and we're left with 15. Okay, e to the ln 25, well, the e and the ln cancel each other out, and we are left with 25. Okay, so now we want to write these, instead of products or quotients, we want to write them as sums or differences. So this one is a product, so we are going to have log base 3 of x plus 1 plus log base 3 of x plus 2 squared, and we're going to bring this exponent down in front. So we have log base 3 of x plus 1 plus 2 log base 3 of x plus 2. And sorry, I just misdid that. That should be a negative right there, and this should also be a negative. Okay, redoing this difference one, because it's a quotient, we have log base 5 of x squared y cubed minus log base 5. Now remember, the square root of z is z to the 1/2 power. Okay, this first logarithm has an x squared times a y cubed for its argument, so that becomes a sum. We have log base 5 of x squared plus log base 5 of y cubed minus log base 5 of z to the 1/2. Now we can just bring all our exponents down in front, so we have 2 log base 5 of x plus 3 log base 5 of y minus 1/2 log base 5 of z. Okay, so that was breaking up products and quotients into sums and differences. Now let's go back the other way. So here we have an addition. That means we're going to change it into a product. So we have log base 2 of x times x minus 3. This one's a difference, which means it becomes a quotient. But first, we have to do something with these coefficients. So we're going to turn them back into exponents. So we have log base 6 of z cubed minus log base 6 of y squared and that's going to equal log base 6 of z cubed over y squared. Okay, and this last one, it looks like we have product and quotient because we have one sum and one difference. So we have the natural log of x minus 2 plus the natural log of x to the 1/2 minus the natural log of x plus 3 to the 5th. Okay, we turn this first part, since it's a sum, into a product. So we have the natural log of x to the 1/2 times x minus 2 minus the natural log of x plus 3 to the 5th. And then changing this difference into a quotient, we have the natural log. In the numerator, we have x to the 1/2 times x minus 2. And in the denominator, we have x plus 3 to the 5th. Okay, moving on to the last page. Okay, we have the following properties that we need to pay attention to. So if m equals n, then log base a of m equals log base a of n. And if log base a of m equals log base a of n, then the m has to equal the n. Now, the a's have to be positive real numbers greater than 1. If a and b are positive real numbers, and neither one is equal to 1, then if we need to change the base, let's say 2 base b, then the change of base formula says log base b of m over log base b of our old base a. Now, why would we ever want to use the change of base formula? Well, it's really the only reason is to use the calculator. The calculator only has log base 10 and natural log functions. So if we need to calculate something that's in any other base other than e or 10, whoops, that's an L, calculator, then we have to use the change of base formula so we can put it in our calculator. So for example, approximate this. Well, I'm going to change it to base e. So that means I have the natural log of 12 over the natural log of 3. And if I put that in the calculator, I get approximately 2.2619. Okay, log base 7 of 325 is the natural log of 325 over the natural log of 7, which equals approximately 2.9723 when we use the calculator. So let's summarize the log properties one more time. Log base A of 1 is always 0. Log base A of A is 1. A to the log A of m power is m. Log base A of A to the r power is r. Log of m times m is log of m plus log of n. Log of m divided by n is log of m minus log of n. Log a of m to the r is r log base a of m. If m equals n, then log base a of m equals log base a of n. And if log base a of m equals log base a of n, then m has to equal n. And the change of base formula says the log of the new base of the argument and the log with the new base of the old base in the denominator. That is the end of 6.5.